In this video, we will have illustration for Theorem 6.5.1. We'll consider V to be R7. Then obviously dimension of V is 7. And let us take V1, V2, V3 and so on V7 to be a basis of V. And let T from V to V be defined in this way. Let V1 be taken to 0, V2 to V1, V3 to V2, V4 to V3. V5 let it be taken to 0 and V6 to V5, V7 let it be taken to 0. Then it can be easily verified that this T is a linear transformation and the matrix of T is this. And we can also check whether it is a nilpotent transformation. We can see that it is nilpotent with index of nilpotence 4. So matrix being nilpotent, corresponding transformation should also be nilpotent with index of nilpotence 4. Now we are going to give an illustration for Theorem 6.5.1. There we first took V to be a member of capital V such that V, Vt, Vt square and so on Vt power n1 minus 1 to be a linearly independent. We first proved, then basis and so on. So like that here we shall consider instead of V is Z. So let Vz be V4. Then we consider Z, Zt square, Zt cube. Index of nilpotence there it was n1, so up to n1 minus 1 that we considered there. Here n1 is 4, so 4 minus 1, 3. So when we consider this, Z when it is taken as V4, here V4t is V3. V4 Z is V4, that's written. V4t is V3 and V3t is V2. V2t is V1. So we have these four vectors as V1 to V2, V3, V4. Now we'll denote capital V1. That is in the same way only there also when we proved the theorem, we considered V1 as span of those vectors only. We proved in first claim that these are linearly independent. So and then V1 we took as span of this. So here also we are taking span of V1, V2, V3, V4 as V1. Obviously dimension of V1 is 4 because they span and they are linearly independent. And V1 is invariant under T, that can also be checked. Then W we are going to choose a span of V5, V6, V7. Then dimension of W is 3 and W is invariant under T. See, these form subset of linearly independent set of vectors and therefore must be linearly independent. Now dimension of W is 3 and it can be easily verified that W is invariant under T. Now V is the direct sum of V1 and W. When you consider the span of this and this, the union of them will span the given capital V and they are linearly independent. So we have our capital V to be the direct sum of these two. And other than zero vectors being in the span, 0 should be there. So obviously intersection consists of singleton 0 and they together span our capital V. So repeating the argument used for V, we use it for W. So we shall take Z as V6. So that V6t is V5. So we have this. Now you choose your V2 as span of V5, V6. Then dimension of V2 is 2 and V2 is invariant under T. That can be checked. Now choose your W prime as span of V7. Then dimension of W prime is 1 and W prime is invariant under T. V7t is 0. So you have now what we did over V. What did we do? We had V to be V1 and W. So now that W is V2 direct sum W prime. The process stops at this stage because you have W because further you cannot split this. So the process stops at this stage. Renaming W prime as V3, what we have is B is direct sum of V1 and W. W is direct sum of V2 and W prime. W prime is renamed as V3. So V is the direct sum of this. And N1, N2, N3 are respectively 4, 2, and 1. And the sum N1 plus N2 plus N3 is 4 plus 2 plus 1, that is 7. And that is considered as the dimension of V. So this gives an illustration for the theorem 6.5.1 in nilpotent transformation. Thank you.